Welcome to the Explainer. Okay, what if the next giant leap in battery tech isn't about some new wonder material, but about, well, building a better battery from the inside out? Today, we're looking at a fascinating paper that uses lasers to carve out little superhighways for electricity, and it could seriously change everything from our phones to our electric cars. You know, for decades, whenever we've talked about a better battery, it's always been a chemistry problem, right? Finding new materials. But what if we've been asking the wrong question all along? This new research suggests the real breakthrough might not be in what our batteries are made of, but in how they're shaped on a microscopic level.
So the logic for getting more range in an EV seems super straightforward. If you want to store more energy, you just need to pack more of the active stuff into the battery. And the easiest way to do that? Just make the components, the electrodes, thicker. Simple enough.
Yeah, but here's the catch. This creates a really fundamental problem. See, thicker electrodes can pack in way more energy, but they also create a massive traffic jam for the lithium ions that are trying to move around and carry the charge. This gives us that classic trade-off. You can have more energy, or you can have more power, but getting both at the same time has been incredibly difficult.
And look, this isn't just a small inconvenience. This is the core challenge that scientists are racing to solve. It's a major roadblock for the next generation of really powerful batteries.
This slowdown has a name. It's called a transport limitation. And honestly, the best way to think about it is exactly like a massive traffic jam. In a thick electrode, the poor little ions have to navigate this long, winding, congested road just to get from one side to the other. And that gridlock absolutely kills performance, especially when you need power fast, like during quick charging.
And hey, don't just take my word for it. This isn't just some theory. As this quote from another study shows, the drop in performance is dramatic. Just tripling the electrode thickness can cause a catastrophic decline. It just confirms that this ion traffic jam is a very, very real problem. Okay, so if we know making electrodes thicker creates this internal traffic nightmare, how in the world do you solve it? Well, this team of researchers came up with a solution that is just brilliant and surprisingly elegant. This is where it gets really clever. Instead of inventing some new exotic material, they used a new tool, an ultra-fast, high-precision femtosecond laser. They're basically using a manufacturing fix for what is really an architectural problem inside the battery. And the process itself, it's just awesome. You start with your regular old thick electrode. Then, this laser comes in and zaps the surface, carving out a perfect grid of microscopic channels. These tiny little grooves act like superhighways for the ions, giving them a direct, clear path deep into the electrode so they can completely bypass all that congestion. But here's where things get really interesting and a little more nuanced. The researchers found that these laser-edged highways, well, they aren't a magic bullet for every situation. They only really work their magic under very specific conditions. For example, take a look at what happens with thin electrodes. We're talking around 50 micrometers thick, about half the thickness of a human hair. Here, the laser-structured version actually performs a tiny bit worse. And why is that? Well, when the electrode is already thin, there's no traffic jam to solve in the first place. All the laser does is remove a little bit of that precious material you need to store energy. But now look at the thick electrodes. This is where it gets really exciting. Under high power, the normal, unstructured electrode just tanks. It loses a huge chunk of its performance, dropping all the way to 65%. But the structured version? It's holding strong at 95% of its capacity. Those express lanes are working exactly like they're supposed to, keeping performance high even when you push it hard. So the huge takeaway here is this. Laser structuring isn't really for the kinds of batteries we have today. It's a technology designed specifically for the thicker, higher energy density batteries of tomorrow. It solves a problem that only really shows up when you start pushing the boundaries of how much energy you can pack into a small space. But the researchers didn't stop there. They asked a brilliant follow-up question. Okay, so we've built a better highway system for the ions. What happens if we also give them faster cars? So they ran simulations combining their laser-structured electrodes with this advanced electrolyte fluid, known as Gen 2. Basically, it's just a souped-up electrolyte. It's chemically superior, which just means ions can move through it way, way faster, period. And this is where it all comes together so beautifully, is the power of synergy. When they paired the physical structure, those laser-etched channels, with the better chemistry of the Gen 2 electrolyte, the ion traffic jam problem, it pretty much just disappeared. The faster cars on the brand new superhighway created a system with almost no congestion at all.
So what does all this geeky science stuff mean for us, the people who actually want to use these things? Well, it boils down to two things that we all care about: faster and much, much safer charging.
The study found that because there was so much less internal resistance, the laser-structured electrode was over 2 times more efficient during charging. That means more of the energy you're pulling from the wall actually makes it into your battery, and less of it is wasted as heat. It just gets in there faster and better.
But speed is only half the story. And honestly, this next part might be the single biggest discovery here, because it addresses a fundamental safety risk in basically all lithium-ion batteries.
That risk is called lithium plating. You see, during fast charging, that ion traffic jam can get so bad that the lithium ions basically crash and pile up on the surface of the anode. They form these sharp, metallic spikes called dendrites. This permanently wrecks the battery's capacity, and in the worst-case scenario, these spikes can pierce the separator inside and cause a short circuit, and yeah, a fire. And the difference here is just incredible. In a normal electrode, that internal pressure, what scientists call polarization, builds up really fast, and that's what causes those dangerous lithium spikes to form. But in the laser-structured electrode, those express lanes act like little pressure relief valves. The stress stays low, and that dangerous plating is completely stopped in its tracks. This is a huge, huge step towards making ultra-fast charging actually safe.
So at the end of the day, what this research really shows us is that the next great leap in batteries might not come from a chemist's lab, but from an engineer's laser. By intelligently designing the internal 3D architecture of a battery, we can unlock the true potential of these thicker, higher-energy electrodes, making them not just more powerful, but a whole lot safer too. It really makes you wonder what other breakthroughs are just waiting for us, not in what our batteries are made of, but in how they're built.